Hello, my name is Agustín del Prado. I'm a researcher for the BASED Center for Climate Change in Spain. The title of my presentation today is Small Ruminants Assessment of the Greenhouse Gas Methane using the GWP star metrics. Just to mention that this work is being now in revision for the Journal of Dairy Research, and if you want to know more details of this work, this will be there hopefully coming up soon. So first, historical greenhouse gas emissions trends in Europe for sheep and goat production have been reduced, and this is for methane, at about 3% emissions per year. This reduction has been very sharp in the first decade, and then it had become more stable. Some of this reduction is due to a drop in animal numbers in Europe, and also has been caused by improvement in productivity and reproduction performance. These estimates are part of a study that we have carried out in the Ice Age project. This is an H2020 EU-funded project. And in order to do these estimations, we use FAOSTAT activity data, and we use the methodology, the latest methodology from the IPCC. So it's the IPCC 2019 refinement to the IPCC 2006 guidelines. So the first question of my talk is, how much has this methane that I have just shown to you, that is being emitted by small ruminants, has contributed to warming the atmosphere in this period, the 1990-2016? And in order to try to answer that, first I would like to mention something about how we estimate generally emissions and their effect into warming from different gases. So conventionally, we generally use the global warming potential. This GWP, or global warming potential, allow us to make comparisons of the global warming impacts of different gases. So specifically, it's a measure of how much energy the emissions of 1 ton of a gas will absorb over a given period of time, relative to 1 ton of carbon dioxide, so CO2. And the time period that we usually do for these comparisons of GWP is 100 years. So GWP provides a common unit of measure, which in turn allows analysts to add up emissions estimates of different gases. So for example, to compile a national greenhouse gas inventory. Also very useful for policymakers to compare emission reduction opportunities across sectors or gases. And in this sense, for example, methane, which is a short-lived gas, is estimated to have a GWP of 28 to 36 over 100 years. So this would be 28, would be reflecting 28 times more global warming potential than CO2. And there is a peculiarity about the methane compared to CO2. For example, or N2O. Methane is emitted today, would last about 12 years in the atmosphere. Then after that, it will disappear. This is much less time than CO2 that lasts for 100 years, or N2O that lasts for about 100 years in the atmosphere. So we need to take into account, it's true that the methane also absorbs a lot of much more energy than CO2 in this atmosphere, the time that it's out there. So the net effect of this shorter lifetime compared to CO2 and higher energy absorption is intended to be reflected in this GWP with the value to 28. So for N2O, for example, nitrous oxide, the GWP value, and this is for the 5th assessment report, the same as the one that I mentioned for methane, is about 265 times. That would be 265 times more global warming potential than CO2, which is the gas of reference. So we have to say that GWP is a simplified representation of the impact of radiative forcing, which in turn influences temperature, but it's really not a direct interpretation of temperature change, and this has been under the debate of the metrics of global warming potential since decades in the IPCC. Currently, unfortunately, there is, however, a new metric, the GWP star. It comes from the GWP and has been developed by a team in the University of Oxford. and is trying to capture this methane's short-lived behavior. And this is trying to better reflect its climate impact than the GWP seems to be doing. So the equation is shown here, how to calculate this GWP star, where CO2 equivalence here would be equal to the GWP value in CO2 equivalence multiplied by one heavily weighted term here that considers the change in methane emissions rate, which is the main driver for temperature changes from methane emissions, and smaller term that is weighted much weaklier, and it's actually the term that you use generally when you use conventionally the GWP 100. So some of this information is coming from these papers and this video that I would recommend if you want to get more understanding on this new metric. But in the next slide, I will show you the repercussions of using GWP star instead of using the conventional GWP as we have been using so far. So here we have three scenarios to show how methane impacts on the climate system and how this is reflected in the metrics. These are examples are also coming from the University of Oxford team. So I actually, this is this in some of these documents here. So we have the top scenario that there is increasing emissions by 25% in these 30 years. Okay, and this is we are talking about methane emissions. So the middle scenario would be leading to very small reductions in emissions. So it's about 0.3% annually. And the bottom scenario would be leading to large reduction of methane emissions of about 25% in 30 years. So if we run each of these scenarios in a climate model, we will have that the top scenario would be leading to warming in these 30 years. The middle scenario of this 0.3% small drop would be annually, would be leading to stable scenario in terms of warming. And the last, the down scenario, the bottom scenario, which is a fast drop in methane emissions, would be leading to a cooling scenario for these 30 years. So, but if we convert these three scenarios using GWP 100 or the conventional GWP, the standard metric for the three scenarios, if we look at the amount of CO2 equivalents, and we'll have all of them shown here, you will have that all seem to be warming irrespective of being a reduction or increase. Of course, those that are increasing more emissions would be leading to bigger warming. But in all the three cases, you would be having a warming result. This contrasts with using the new metrics, the GWP star, where if you equate these different emissions of methane changing in time, you would have this kind of result. This kind of result that it would be much more similar to the result that you would have using a climate model. So, for example, in this situation where you were having a drop of 25% of emissions of methane emissions in 30 years, you would already be having reflected in GWP star a cooling scenario and equivalent to removing some CO2 from the atmosphere. So in this sense, if we try to use the GWP 100, the conventional, in our reduction, in our graph that we showed at the beginning of this presentation, then we will have this net average CO2 equivalents per year in kilotons, and then you would be leading to a warming situation. So like I've shown before. So if we use the new metrics, the GWP star, and remember that how these emissions have been reduced at the rate of here very drastic and then constant, but the average of these years is about 3% annually. This new metric, GWP star, that is capable of linking the emissions to warming results, would have shown that this drop in emissions would have not added much warming, but instead would have been cooling in this period of time. So this contrasts with any analysis being made by GWP 100 that I showed before, where small ruminants always appear as high emitters, especially if we think about static GWP-based carbon footprint. So this leads to our second question. So how much of the warming would be added to the atmosphere in a future period, 2005-2050, if we maintain the rates, or even we could manage to decrease the rates of methane by 1% in this small ruminants production. So here I have the results. So using the GWP star metrics in Europe, by having constant methane emissions from now on, we could stabilize the warming effect of methane from sheep and goats in the period studied, and shrinking sheep methane by even more, 100% annually, would be even contributing to a larger cooling effect. This would be very much contrasting with if we did the same reduction in the amount and rate in terms of CO2 equivalents. So this would be 1% per year, but not coming from methane, but coming from CO2 from fossil fuels. We would still be getting a large increase in the effect of this CO2 in the net warming. CO2, as I previously mentioned, lasts hundreds of years in the atmosphere compared to the effect of the methane that after 12 years it disappears. So this would be the different effect that you would find with GWP star. So my third question, in this case, I'm going to be talking already about the specific dairy, sheep and goat sector. So I'm now making the same question, the first question that I did. So how much warming is associated to this sector, specifically the dairy sector, but not just talking about the direct emissions, so methane emissions, but thinking in terms of the whole carbon footprint. So taking into account CO2 from fossil fuels, CO2 from possibly impacts in land use change in other countries through feed import, and also in terms of energy use, and also in terms of N2O, and also in terms of direct emissions like methane. So in order to have an approximation of the historical warming associated to dairy, sheep and goats in Europe, we need first to have their historical LCA-based greenhouse gas emissions. And to our knowledge and date, there is not such a calculations for this period of time and small ruminants. There are, however, LCA-based European calculations for single years. So I have two examples here, two big studies, one from FAO, so Gerber and collaborators, 2013, using data from 2010, and Waste and Leib and collaborators, 2010, that they are using emissions from 2004, and they are using the whole small ruminants as an aggregated value, and that's for EU27. And the FAO study, they use the European FAO area, and they separate between carbon footprint of milk from sheep, carbon footprint of milk from goat, and also in terms of different production systems. So like we can see here, the carbon footprint and the separation of the different gases impact for grassland-based or mixed-based dairy, sheep, and dairy goat systems. So from the carbon footprint value of, for example, 2010 from Gerber and collaborators, 2013 from FAO, in attempt to derive historical European emissions, we have used a combination of information and assumptions. So first, we use historical data on changes in productivity and parameters for Spanish sheep and goats as a proxy of how European production systems may have changed in the last decades. And we applied for these changes the specific information from different carbon footprints of different breeds and production systems in Spain. This information was used to extrapolate the carbon footprint estimated in 2010 by FAO to the period 1990 to 2018. This carbon footprint then was scaled in total carbon footprint, at the European level by multiplying the carbon footprint of the milk by the total amount of milk for each of the years as estimated by FAO-Stat. So this is meant not to be a very robust estimation, but a possible approximation of how much the emissions have been changed. Especially very interesting to know how the proportion of CO2, methane, and N2O may have changed using Spain as a proxy, as there was no other better information. So for the receipt, here is the range of greenhouse gas results for 1990-2018 in CO2 equivalence emissions, comprising methane, N2O, and CO2 emissions. And this is for the carbon footprint of European dairy production. So this goes from about 11 to 13 megaton CO2 equivalents per year to about 8 in the last years. Just consider that this range of possible emissions become closer to zero. So the uncertainty is lower here. It's just because we are using the 2010 as a year to extrapolate the rest of the years. So if we had used the GWP conventional for assessing warming, we would be aggregating all CO2 equivalent emissions from year to year, finding that this would have been the impact of warming in reference to the warming already caused in 1990. So they would be accumulating about 0.25 milli degrees in terms of warming up to 2018. However, if we apply the GWP star methodology, the warming results are completely different. And we see that for most of our estimates, historical emissions accounted for not just methane, but also for N2O and CO2 from fossil fuels and land use change. These emissions would lead to a reduction in warming for most of the decades. Like we can see here, there is some potential increase of emissions, but compared to the previous one, which was up to 0.30, in this case, we are getting almost negligible to negative warming associated to this change in emissions. And similarly, with dairy goats, we have much lower values of CO2 equivalent emissions and also lower warming associated, but it's just because it's a much smaller volume. But again, if we aggregate CO2 equivalents into warming with using GWP conventional, we have this, almost 0.10. And if we use GWP star, we still have some warming, but it's much smaller than it has been estimated as GWP. So we're talking about 0.10 against the maximum 0.02. And in some areas, some first year, there was a possibility of some cooling effect of the dairy goats farming systems. So if we do this exercise with the EU27 data based on LAPE and collaborators from 2010, this study, we obtained that for some years, for the whole unaggregated small ruminants, and this is 2004, and this is using other assumptions, etc. But we can see that for many years, there was a net decrease of the warming compared to the 1990 reference. There was also some warming in some years, but still very, very small warming for those years that there was a little bit of warming. So this leads to our fourth question. So if we look at the future, how much warming would be expected for the European dairy sheep sector and carbon footprint if we don't change our global production? And in a second situation, if we introduce some kind of greenhouse gas mitigation. And for illustration purposes, and as an example of this mitigation measure, we have just simulated the dairy sheep production systems in the European FAO region. And we are simulating that there is a gradual, slow or fast introduction of this additive, which is the 3-NOP, that has been shown to reduce in sheep about 30% methane emissions. So these are the results in warming for the year 2010 to 2100. And applying this GWP star methodology, we can see that this would be the warming associated to no changes in productivity in whole production in Europe. This would be in black the warming associated to a slow introduction. So that would mean that we would have all the farms gradually with this additive in 2080, and the fast introduction that would be leading already some zero warming effect up to 2060 about would be represented by this fast introduction would be leading by using an introduction of this 3-knob additive in all farms by 2040. Now, a last question. Some ship systems in Europe are associated with grassland, so we understand that there could be, that we could also argue that there is some soil organic sequestration potential that we have not yet included in the whole equation. So we're trying to assess that. What if we include the soil organic carbon sequestration? And we want to make sure that we also talk that we understand that there are some limitations and that changes in grassland management we know can lead to carbon sequestration in the soil, and this is shown in this beautiful graph that comes from Grace and Confused study by Oxford University as well. So these changes in carbon are rapid at first, and then they tend to reach an equilibrium in which the carbon entering the system is equal to that leaving the soil after some decades. However, and that's that's something that we need to bear in mind, these gains from sequestration could be reversed later if we do poor management. So we are assuming that there is no poor management, and we are taking into account this average effect of soil or carbon sequestration potentially attributed to our systems. And for example, we are using, so we know that for different ruminant livestock products in Spain, and this is coming from extensive and semi-extensive systems. And these ranges that I'm showing here come from the analysis of different studies, peer-reviewed international studies that have been evaluating the carbon footprint and the potential soil organic carbon in these systems. So there is an estimation of the percentage carbon footprint that can be offset by this soil organic carbon in these different production systems. So for dairy sheep and dairy goat, we see that there is large potential for sheep up to 90% of offsetting the carbon footprint. And we have seen that for dairy goat is almost 40%. So there is large ranges, but there are some possibilities. So when we do the warming calculation, for the scenarios that we introduced before with the 3-knob additive, and we account for the estimated soil organic carbon sequestration, we found that for the period 2020-2100, there is no additional warming if we maintain the same productivity as in 2020, but we introduced either slow introduction of this 3-knob and accounting for soil organic carbon. So this is a tiny warming associated, but if we do a fast introduction, there is a sharp cooling effect for this period of time. So this contrasts to the scenario where we were not accounting the soil organic carbon sequestration. So with this, I am already at my final slide with some conclusions where I can say that the European sheep and goats have not caused additional warming to the atmosphere, as I have shown here with the GWP star metric. This in the last decades and from direct greenhouse gas emissions and small, if we think about the whole carbon footprint. They have, if we think about dairy production, have caused very small additional warming since this 1990. And we have tested that any strategy towards climate neutrality should consider separating methane from long-lived greenhouse gas emissions using this GWP star metrics, and also we should account for potential soil organic carbon sequestration in pastures. So I also think I have shown interesting scenarios where greenhouse gas mitigations can actually provide great climate benefits in the sector. Thank you very much.